A city where the ground floor sits on the ocean, where 2 million people live inside a single structure, suspended above Tokyo Bay, anchored to the seafloor by foundations that reach down into rock no one has ever built on before. That is what Japan's architects and engineers proposed, and they were completely serious. Tokyo is running out of room. The Greater Tokyo metropolitan area already holds more than 37 million people, pressed into a coastal basin ringed by mountains on one side and open water on the other. Land prices in central districts have climbed so steeply that entire neighborhoods have stopped growing upward and started discussing whether to grow outward onto the sea. This was not a new thought. Japan has been reclaiming land from Tokyo Bay since the Edo period. But what a consortium of construction firms, planners, and engineers proposed in the 1980s and revisited in subsequent decades was something entirely different. Not reclamation, not an island, a pyramid. The project is called Tri 2026, though its original name, Tri 2017, dates the concept to an era when the year 2000 still felt far away. The Shimizu Corporation, one of Japan's largest general contractors, produced the original design proposal. Their plan described a self-contained floating city in the form of a colossal pyramid structure, reported to accommodate around 750,000 to 2 million residents, depending on the design phase. The cost estimate attached to the proposal was roughly $500 billion. Not a development loan, not a phased budget. A single construction figure of almost unimaginable scale. For context, the entire annual gross domestic product of Sweden is around $550 billion. Shimizu's engineers did not arrive at the pyramid shape for aesthetic reasons. The choice was load distribution. A pyramid spreads its weight across a base rather than concentrating mass on a single foundation point. In open water, with no bedrock available at usable depth near the surface, distributing load was not optional. It was the only structural logic that worked. The proposed structure would stand at 2 kilometers high, 2,000 meters from its base platform to its apex. That makes it roughly 14 times the height of the Tokyo Skytree, itself one of the tallest structures on Earth. The base alone would span 6 kilometers per side. Inside this structure, the designers envisioned something that functioned less like a building and more like a compressed geography. Residential blocks arranged in vertical neighborhoods, each cluster grouped around internal transit corridors, shopping areas, parks, and public plazas, all contained inside the pyramid's outer shell. Transportation between levels would run on magnetic rail systems, moving residents vertically and horizontally without surface roads. Power generation would draw on solar panels lining the pyramid's outer faces, supplemented by wave energy captured at the base platform. The aim was a city that produced most of its own electricity, managed its own water systems, and circulated people without cars. But the math still would not work. Not because the vision was incoherent, because the materials to build it did not exist in the 1980s, and some of them barely exist now. A structure 2 kilometers tall and 6 kilometers wide, floating on Tokyo Bay, would need to resist earthquake loading unlike anything a land-based building encounters. Japan sits at the intersection of 4 tectonic plates. The region around Tokyo has experienced some of the most destructive earthquakes ever recorded, including the 1923 Great Kanto earthquake that killed an estimated 105,000 people and destroyed much of the old city. A floating pyramid in that same bay would need to flex, not resist. Rigid structures of that mass would shatter under seismic loading. The entire structural philosophy would need to accommodate movement rather than fight it. Shimizu's engineers recognized this constraint and built it into the design from early on. The internal framework they proposed used a lattice of modular trusses, prefabricated components that could be assembled at sea, connected incrementally, and theoretically replaced or reinforced section by section as the structure grew upward over decades of construction. The estimated build time was somewhere between 30 and 100 years, depending on financing pace and materials availability. 100 years of continuous construction, in open water, in earthquake country. No single corporation on Earth has the capital to attempt it alone. No government has authorized the spending. The proposal remains what it has always been, a technically documented vision of what might be possible, waiting for the moment when the conditions to pursue it finally converge. In April of 2011, roughly 1 month after the Tohoku earthquake and tsunami reshaped Japan's sense of its own vulnerability, Shimizu Corporation released an updated presentation of the TRY 2026 concept. The timing was deliberate. The earthquake had killed nearly 20,000 people. It had exposed how fragile Japan's coastal infrastructure could be under extreme seismic and wave loading, and it had renewed a very old Japanese conversation about whether future cities should sit on land at all. Shimizu's presentation did not say any of this directly. It did not need to. The proposal spoke for itself. The engineering challenges that made 1980s observers dismiss the concept have not disappeared, but several of them have moved. Carbon fiber composite materials, which barely existed in structural applications in the 1980s, now appear in bridges and aerospace frames. Ultra-high performance concrete can now achieve compressive strengths 10 times that of standard construction concrete. Three-dimensional additive manufacturing, large-scale fabrication using robotic systems, has produced structural components in ways that assembly line methods never could. None of this solves the pyramid, but each development moves one obstacle slightly further from impossible. What makes the TRI proposal unusual is not ambition alone. Japan has a long and specific tradition of speculative engineering at national scale. The Seikon Tunnel connecting Honshu to Hokkaido, completed in 1988, was for years the longest undersea rail tunnel in the world. The Akashi Kaikyo Bridge, completed in 1998, remains the longest suspension bridge span ever built. These projects were dismissed as fantasy before they were built. They were called economically indefensible. They were called structurally impossible. They exist. The TRI proposal is different in one critical way. Those earlier mega projects required no new physics, only engineering at new scales. The Pyramid City in Tokyo Bay requires materials and construction methods that currently exist at prototype or near prototype stage, not industrial scale. That gap is smaller than it was in 1988. It is not yet closed. There is a human dimension to this proposal that the engineering specifications tend to obscure. Japan's population is declining. The country's total population has been falling since around 2010. The Tokyo metro area still holds together through internal migration from rural prefectures, but demographers project that even Tokyo's population will fall in coming decades. A city designed for 2 million people, built at $500 billion, in a country whose overall population is contracting, the economic logic requires an explanation that goes beyond housing existing residents. Shimizu and other proponents have pointed toward this explicitly. The Pyramid City concept is not imagined as a solution to Japanese overcrowding. It is imagined as an exportable model, proof that humanity can build habitable density on non-land surfaces, applicable to coastal megacities across Southeast Asia, South Asia, and eventually to islands and coastlines that current climate projections suggest may become uninhabitable in their present form. The pyramid is not a building. It is a proposal about where cities go next. There is still no funding agreement. There is still no government authorization. Shimizu has continued refining design documents across multiple decades, updating material specifications and cost modeling as construction technology evolves. Whether the project moves forward in the 2030s or remains a design study for another 50 years depends on converging pressures, land scarcity, sea level trends, and the willingness of some consortium of public and private capital to commit to a construction timeline measured in generations rather than years. Japan has done that before. The Seikon Tunnel took 24 years from groundbreaking to opening. The people who approved it knew they would not see it finished. A structure 2 kilometers tall rises above the cloud layer at certain seasons. It would be visible from satellites as clearly as any natural geological feature. Inside, neighborhoods would exist that had never touched dry land. Children would grow up in a city that the sea surrounds on every side and supports from below. Whether that city ever gets built, the proposal itself has already done something. It placed a specific, engineered answer on the table for one of the defining questions of the coming century: what to do when there is no more room on land. The answer involves a pyramid in a bay, and a century of work, and materials not quite finished being invented. Whether it finishes or fails, it will leave a mark on how the next generation builds.